All right, greetings everyone. I'm going to make a couple videos showing where certain volume formulas come from that we typically would get in geometry, just to illustrate some of the processes we've learned here in calculus. This I would have done in class if we had a little bit more time to work on volume, but we were, as you know, we were rushing, and I wanted to, get on to other things, make sure we covered all the material by that certain date. So let's go through an example of where the formula for the volume of a sphere comes from. This is just an example. I mean, this can be derived in other ways, but I'm going to use some calculus to derive this formula, and you get to see some application of what we learned in class. Well, first of all, we have to think of how we actually generated solids in calculus. And we did either volumes with a certain base and a known cross-section, so of a certain shape, or we did volumes by rotating a certain area about an axis. And so we're going to use that technique. We could do it with a volume with a known cross-section, and maybe I'll do that later as another video. We kind of did it in class once, but we'll see. So what shape, imagine for yourself, what shape would I have to rotate around some axis in order to create a sphere? What two-dimensional shape would we rotate to create a sphere? Well, you can pause and think about that for a moment if you want to come up with your own answer, but I think everybody would fairly quickly come up with the idea that we'd have to rotate a semicircle. If I rotate a semicircle around an axis, that's going to sweep out the volume of a sphere. So what I need to do is find this volume by thinking about rotating this semicircle around I'm going to use the x-axis here. So let's suppose we have a circle of radius r and centered at the origin, and so this intersects at r and negative r, and then this is going to be up here at r as well. And so what I'm going to do is I'm going to take a rectangle in this picture, or for this picture, and since I'm rotating around the x-axis, I'm going to have a delta x like this. And so if you think about what method for revolving I would use, discs or washers, I hope you can clearly see that I would be using discs, because any rectangle that I draw wherever along this region here, its bottom side is always going to be bounded by the axis of revolution, the x-axis here, and so there are no gaps, and so there's no reason to use, no need to use a washer method. All right, so what I need here is an equation for this, because the height of this rectangle, which is going to end up being the radius of our circular cross-section, is given by this function. And so if we recall from geometry, the equation of a circle centered at the origin is x squared plus y squared equals the radius squared, so in this case equals r squared. And so if we solve this for y, of course we get a plus or minus the square root of r squared minus x squared, but I'm not going to put the plus or minus because I'm just going to be revolving the upper half of the semicircle in order to get the volume. By rotating the upper half, I sweep through what the bottom half would cover anyways, and so I just need the upper half in the revolution. Now remember, the key to volume is to integrate over our region A to B the area of the cross-section as a function of x. And since when we revolve and see what we form, as we said, we're going to see discs, and so the area that we're finding right here, the area of our cross-section, is just the area of a circular disc, which of course we know is going to be pi times radius squared. And so, in this case, our radius is going to be the function root r squared minus x squared. So the area of our cross-section is going to be pi times the square root of r squared minus x squared, quantity squared. But of course the square and the square root are going to cancel, and so we're going to be left with pi times r squared minus x squared. And so now to find the volume, I just need to integrate from negative r to r, pi times this r squared minus x squared with respect to x. Don't forget your dx, folks, because that's going to be important in this evaluation. Now, just one little shortcut I'm going to use is to recall that we have symmetry here in this picture. We have reflection symmetry about the y-axis, and so if I figure out the volume from 0 to r in this region over here, I'd get the same, and then to figure out the volume from negative r to 0 this side over here, I get exactly the same thing because of that symmetry. So all I really need to do is double the integral from 0 to r of this r squared minus x squared dx. That way, when I take my antiderivative, I need to evaluate at r and 0, which will save me a little bit of work evaluating at 0. Now, in order to evaluate this, we need to use the evaluation theorem, and so we need to find or the fundamental theorem. We need to find an antiderivative of the r squared minus x squared term. And this is where it's important that you remember to put the dx, because the dx here tells you what the variable of integration is, what we're integrating with respect to. And so we're integrating with respect to x. We should know that r is just a constant. And so a common mistake that some students would make is to take the antiderivative of r squared with respect to x as 1/3 r cubed. That's wrong, because r is not the variable here. R is just a constant. And so when we take our antiderivative, of course we're going to get 2, and then ooh, what did I forget? I forgot to write pi right there. Or in next to the 2, one of the two. Let me go stick it in over here. Sorry about that, my little error. Hopefully you caught that and were just yelling at the screen telling me, hey, that I was wrong. It'd be good for me to hear it. Alright, so now, integrating r squared with respect to x. R squared is just a constant, so the antiderivative of a constant is going to be that constant times x. And then we're going to take the antiderivative of x squared with respect to x. We'll get a 1/3 x cubed. And we're going to evaluate this from 0 to r. And so, plugging in r in place of all the x's, we'll get an r cubed minus 1/3 r cubed. Now, we've got to plug in 0, but since we got this simple polynomial here, we plug in 0, everything goes to 0. So I got nothing to subtract from that. I'm not even going to write it down. And so we get 2 pi times, well, r cubed minus 1/3 r cubed is going to be 2/3 r cubed. And so 2 pi times 2/3 r cubed is going to be 4/3 pi r cubed. Hopefully you remember that formula from geometry. And that is how you find the volume of a sphere. 4/3 times pi times the radius cubed. All right, go study.